Hello. In this problem, uniformly charged thin spherical shell is given. Now they are saying if you cut this into two hemispherical shells, what force must you apply so that you are actually keeping them together? Okay, so because when you charge the sphere, the entire charge is going to stay on the outer surface. So if you, let's say, cut it into two equal halves, there is a repulsive force which is trying to push the two hemispheres away. So you'll have to apply a force. So in order to answer this question, so what you can do is, uh, let's first figure out if the shell is together. Okay, so you have not made the cut. So without the cut, is there any force acting on, let's say, each part of the shell? So let's take a very small area here. I'm going to draw slightly big, but imagine that I'm taking a tiny area here. So if I imagine, let's say, a tiny cylinder here. So let's pretend that we have a tiny cylinder. Okay, so this is our Gaussian cylinder. Okay, so the area of the cap, okay, so whatever area that we are taking on the surface, let's say that area is delta A, so very small area. Okay, sigma is the charge per unit area. Now, what do we know about uniformly charged spherical shell or a metal shell with charge on it? The electric field inside the shell is zero. Okay, so electric field outside the shell is present. Okay, so we can find the electric field outside the shell. Okay, so in order to find that, what we can do is we can just apply Gauss law here. So there will be some electric field here. There is no electric field inside. Okay, so through the cap, circular cap inside, the flux is zero. And we know that the electric field has to be radially outwards. So through the curved surface of the cylinder, the electric flux again will be zero. So if you apply Gauss law, so the total flux should be the net charge enclosed by epsilon naught. So if you look at the flux is present only through the circular face of the cylinder which is outside the shell. So the flux here is E into delta A. The charge inside the Gaussian cylinder will be sigma into delta A by epsilon naught. So here the electric field is sigma by epsilon naught. Okay, now, but if I, let's say, think about the rest of the charge. Okay, so if I think about the rest of the rest of the charge is definitely doing something in the inside part. Okay, so let's say here. So suppose if I take an area just on the surface of the sphere, so let's say this is the area. So I'm taking 2 points. So let's say one is inside, in, and the other is outside. Outside and inside. Okay, this is the idea that we need to understand. If you are very close to the, let's say, tiny charge, the charge anyway appears very large. I know, I mean, we are saying it is a tiny charge, but the charge anyway appears very large. So because it appears very large, it should apply. Okay, so whatever electric field that you have outside, you should have an electric field inside also. But this is whatever electric field that we are talking about now is not the net electric field. Okay, so the net electric field is simply sigma by epsilon naught. But if I treat this as an infinite sheet of charge, the infinite sheet of charge should actually provide an electric field of sigma by 2 epsilon naught. Okay, so it will provide in both directions. So inwards towards the center of the shell and away from the center of the shell. But by using Gauss law, we are getting this as the electric field. So what this really tells us, again, so you have to really understand here, if I'm very close to the tiny charge, tiny area that I'm talking about, get really close to the tiny area. So when you get that close, it's a tiny area, but its effects will be that of an infinite sheet of charge. Okay, so an infinite sheet of charge will actually provide electric field in both the directions of magnitude sigma by 2 epsilon naught. But we are saying outside we have only sigma by epsilon naught. That is the result that we obtained using Gauss law. That is true. So this is correct. Now this is also correct. So what is really happening here? The rest of the shell. Okay, so there is charge on the rest of the shell. Okay, so this region is not isolated. The rest of the charge is also interacting with it. So the rest of the charge is definitely applying some electric field, so that at the inner part the electric field becomes zero. So what is the electric field that the rest of the shell, the charge on the rest of the shell must be applying? It should apply an electric field in the opposite direction having the same magnitude, so that inside the electric field becomes zero. So the rest of the shell is applying sigma by 2 epsilon naught. Okay, so this is the electric field applied by rest of the charge. Okay, so rest of the charge applies an electric field of this much, and then it cannot just be at one location, right? So the outside point is not very far, so that means at the outside point also it would apply sigma by 2 epsilon naught. And okay, so the tiny sheet of charge is applying sigma by 2 epsilon naught. The rest of the shell is applying sigma by 2 epsilon naught at a point just outside the shell. If you add them factorially, you are getting sigma by epsilon naught. Inside, they are getting cancelled. So that is 0. Okay. So now, what this tells us is, if you take any tiny area, okay, so if we consider any tiny area, let's say like this, the rest of the shell is applying an electric field of sigma by 2 epsilon naught at all points on the tiny area. Okay, so if you consider any tiny area, the rest of the shell, okay, when I say rest of the shell, it is the charge on the rest of the shell is applying an electric field of sigma by 2 epsilon naught on this tiny area. Okay, so now this tiny area has charge. Okay, so what is the charge? Sigma into delta A. So what is the force applied on the tiny area? The force applied on the tiny area will be charge. Okay, so charge multiplied by electric field, which is sigma by 2 epsilon naught. Okay, now this is sigma square by 2 epsilon naught into delta A. Okay, so once you have this force, if I divide this force by area, I will get pressure acting at that location. So this pressure is known as electrostatic pressure. Okay, so it is present everywhere at all points on the shell. So the electrostatic pressure, let's say we'll call that P here. This should be, if I divide this by delta A, so I'll get sigma square by 2 epsilon naught. Okay, so that's the electrostatic pressure. Now, if you consider each hemisphere, the force that each hemisphere will feel will be obtained by multiplying this electrostatic pressure and the projected area of that hemisphere. Okay, so the force, the external force that you must apply to keep these two hemispheres, let's say, in position, will be the electrostatic pressure multiplied by the projected area. Okay, so you can like integrate that and then get this answer, but I think we can just use the projected area. So what will this be? It will be sigma square by 2 epsilon naught into projected area will be pi r square. But luckily, the problem is not really asking us the exact answer. It's just asking proportional to what. So we must have sigma square and then r square. So the answer will be A.